So again, we'll read through the whole thing. A balloon, 30 centimeter diameter, inflated. The radius is increasing at a rate of 3 centimeters per second. So that's telling us that we know that our radius is a function of time, and we know that our change in radius with respect to change in time is 3 centimeters every second. How fast is the surface area of the balloon increasing? I'm just going to use S for surface area. That tells us that surface area is a function of time, and we want to find the change in surface area with respect to the change in time. In particular, we want to find it specifically when the diameter is 30 centimeters. How fast is it increasing when the balloon is 30 centimeters? So what does that tell us about our radius? And we're trying to find it when the radius is 15 centimeters. So this will really test your formula skills. What is the surface area formula? And we're going to imagine this balloon to be spherical, just to make it nice. Surface area of a sphere. 4 pi r squared. Now, one way that, I don't know if this image will help you remember this formula or not, but if you take out a sphere, I have a golf ball here, it's a Jets one, so maybe it's good luck that they're going to win tonight. And surface area is painting the whole outside. Now, if you are to look at it from one perspective, obviously I can't see the back side. And when I look at it in 2 dimensions, can you see that I'd see a circle? Now, I see one circle when I look at it from this side and one circle when I look at it from this side. If you were to spray paint from one side and hit it, it would hit it, but it wouldn't hit all of it because there's some depth to it as well. And in fact, if it was a perfect sphere and it worked out perfectly, when you turned it on top and bottom, you might see completely white still. If it was, you could have paint that wouldn't run and would be so perfectly fine that it would do that. Of course, if you threw paint at it from the side, it would probably cover the whole thing. But it helps me remember this formula because I see from 4 perspectives, from one side and the other side, from the top and the bottom, 4 circles. And that's all this formula is saying, is 4 pi r squared. So it's a visual thing that helps me remember that formula. If you know the volume of a sphere, do you remember that formula? Okay. If you take the derivative of the volume formula, you get the surface area formula. Very cool. Right? Whatever you do a derivative of something, you move down a dimension. Like area of a circle is pi r squared. What's the derivative? The circumference. Pretty cool. Okay, anyways, so we're at surface area. We have our surface area is 4 pi r squared. Since surface area and radius are both functions of time, then we can do the derivative with respect to time of this whole function and use implicit differentiation. So I'm going to take d dt of this whole thing. Well, on the left side, I'll just get ds dt, because the derivative of s would just be 1, and then the derivative of our surface area is ds dt. On this side, we'd have the chain rule, so you'd bring the 2 out in front, 8 pi r, and then derivative of r would be dr dt. We want to find ds dt. We're finding it when the radius is 15, and we're told that it changes at a rate of 3 centimeters per second. And what do we get here? 360 pi? And since that surface area be centimeters squared per second.